Okay, thank you, Raymond, for those words. Not really sure what to say. I never expected to win a prize like this, but now that I have, I'm very happy. I'm very proud to have my name added to the list of past recipients, which includes yourself. I'm also very happy to win a prize that bears the name of Felix Chayes, because it may surprise you for somebody of my generation, but Felix Chayes was actually an important person in my development as a scientist. And in fact, that's the reason why I have decided to talk on the topic of geochronology as a compositional data problem, because I will explain in my presentation how the work of Felix Chayes on ratio correlation is important to geochronology, and how his work actually got me started on this journey to reevaluate geochronological data processing. Now, I am a geologist by training. I'm neither a mathematician nor a statistician. I have taken a number of statistics modules as a student, especially during my PhD at Stanford, and normally when I address an audience of geologists, I can be fairly confident that I know more statistics than most people in my audience, but today I'm not so sure. So I'm a little bit nervous about today's presentation, because I am fully aware that my contributions to geochronology are rather trivial from a statistical point of view. But trivial though they might seem, I think they are important contributions, and I'll try to bring this point across in my presentation. My presentation will consist of two parts. In the first part, I will give you a general introduction to geochronology. I won't assume that you know anything about isotope geochemistry or geochronology. I will go through this relatively quickly because you are a smart audience, and I will introduce various mathematical statistical tools and devices that have been developed by geochronologists to get a better handle on geologic time. And then in part two of my presentation, I will revisit these statistical devices and put them in a compositional data framework. Okay, so that's the structure of my presentation. All right, geochronology is the science and the art of measuring geologic time. Time is a very important concept, by the way, in geology. Geology is, in essence, a historical science, so constraining time is of the utmost importance. And over the past decades, nearly a century, geochronologists have developed an elaborate and extensive toolbox of techniques to measure geologic time, and most of the tools in that toolbox are based on radioactivity. Now, I'm sure you all know that radioactivity is a property of the atomic nucleus, whereby an unstable configuration of protons and neutrons changes into a stable configuration of protons and neutrons through the emission of radiation, alpha, beta, and gamma radiation, which can be detected with a Geiger-Müller counter. Now, the measurement that you read on this gauge here, the amount of radiation, this measurement is proportional to the rate of change of the radioactive parent under the detector. So that's dP dt. And it has been shown time and again that this rate of change is independent of pressure, temperature, chemistry, or any other physical parameter. The only thing that controls the rate of change of the parent is the amount of parent that is present under our detector. So that forms this simple differential equation where the constant of proportionality is negative because we are losing parent through time. Now, you all know that the solution of this differential equation is a simple exponential function which sees the parent decay from an initial amount P0 to 0 with a characteristic timescale, a half-life, that describes the amount of time it takes for P0 to be reduced to P0 divided by 2, P0 divided by 2 to be reduced to P0 divided by 4, etc. The table here lists a number of commonly used parent-daughter pairs with their respective half-lives. You're all familiar with radiocarbon, I assume. radiocarbon, carbon-14, has a half-life of 5,730 years. That's very useful for archaeologists, not so useful for geologists. We are interested in millions to billions of years, and radiocarbon simply is not sufficiently long-lived for that. So we need to use longer-lived radionuclides, such as uranium-235, potassium-40, uranium-238, etc. These have half-lives of hundreds of millions to tens of billions of years. These radionuclides are survivors from the formation of the solar system and the supernova that preceded it. They are barely radioactive at all. If you've got trace amounts of these radionuclides in your sample, the Geiger-Müller counter will barely show any signal. Nevertheless, they are very useful for constraining chronologies, and that is done by rearranging this equation, the solution to our differential equation, in terms of t, which is time. And that requires that we estimate the initial amount of parent that was present in our sample when the clock started ticking. P0 is unknown, but we can estimate it, we can piece it together from the remaining surviving number of atoms of the parent, P, and the current amount of daughter present in our sample, because all the daughter atoms that are present in our sample used to be parent atoms. If you add them back, you can reconstruct P0, and then we can rearrange this equation in terms of the measurable present-day daughter and parent atoms, plus this exponential ingrowth function. So the boxed equation in red is the fundamental ingrowth equation that forms the basis of all the geochronometers that I will be introducing to you in my presentation. So the first chronometer, I will introduce 4 to you. The first chronometer that I would like to talk about is the rubidium-strontium clock. Rubidium is an alkali metal that has 2 isotopes, 85 and 87. 87 is radioactive. It has a half-life of nearly 50 billion years, and it undergoes beta decay to strontium-87. That's an earth alkali metal. Strontium-87 is one of 4 isotopes of strontium. The other 3 do not have a radioactive parent. And they're still very useful to us, as I will show in a minute. So our ingrowth equation here can be simply adapted to this system. We've got the radiogenic strontium-87 on the left, which is a function of the radioactive rubidium-87 present in our sample today times this exponential ingrowth factor. Now, this equation assumes that all the strontium-87 is radiogenic and that there was no strontium-87 in the sample when the clock started ticking. That assumption is generally not correct, and we need to adjust our equation to account for the existence of some initial strontium-87, strontium-87 naught. So then, the total present-day amount of strontium in our sample is the sum of the initial and the radiogenic component. For practical reasons, which I'll get to in a minute, it is useful to normalize the left-hand side and the right-hand side of the equation to a non-radiogenic isotope of strontium, in this case, strontium-86. Strontium-86 does not have a radioactive parent, so every atom of strontium-86 that is present in our sample today was already there when the clock started ticking. So then we get this equation where we have 2 measurable atomic ratios. The ratio of 87 to strontium-86 can be measured, and the rubidium to strontium ratio can also be measured. And we've got 2 unknowns. The initial strontium-87-86, so the non-radiogenic ratio, is unknown, and the age, which is what we're after, is also unknown. 1 equation, 2 unknowns, that's an under-constrained problem. If we want to solve this equation, we need to analyze multiple aliquots, multiple splits of the same sample. For example, multiple cogenetic minerals from the same rock. If they all have the same age, but they vary in their rubidium-strontium ratio, then if you plot these multiple splits of the same sample on a diagram of strontium-87 to strontium-86 against rubidium-87, strontium-86, in this ratio diagram, the points should plot on a line whose intercept allows us to estimate the initial strontium-87-86 ratio and whose slope is a function of the age. This diagram is called an isochron, and it's the bedrock of high-precision geochronology. Now, as you're all mathematicians and statisticians, many of you will probably spot some issues with this diagram, but I will talk about them in part 2 of my presentation. What I would like to do in part 1 is move on to the second chronometer in the toolbox, so I'll be introducing you to 4 of them. The second one is based on the radioactive decay of potassium. Potassium-40, another alkali metal, is radioactive with a half-life of 1.25 billion years. It undergoes branch decay. 90% of potassium-40 decays to calcium-40, and the remaining 10% decays to argon-40, which is a noble gas that accumulates into the atmosphere and constitutes about 1% of the air that we are breathing at this moment. So 1% of the air that you are breathing is the result of the radioactive decay of potassium in the crust and the mantle of the Earth over Earth's history. So we can use exactly the same isochron equation that we used for rubidium-strontium and apply it to the potassium-argon system. So instead of rubidium-87, we've got potassium-40. Instead of strontium-87, we've got argon-40. And instead of strontium-86, we've got argon-36. And then we've got this pre-multiplier here, which did not appear in the rubidium-strontium equation. And that simply accounts for the fact that only 10% of the rubidium decays to argon, the remaining 90% decays to calcium. The potassium-argon method has been around since the 1950s. It's very powerful and very useful, but it has one big disadvantage, and that is that potassium is an alkali metal, argon is a noble gas. They are two completely different chemical elements. They cannot be analyzed on the same machine. So you need 2 machines to measure a potassium-argon age, and you need to have 2 splits of the same sample, which you need to make sure are homogeneous and matched in terms of composition. One is sent to the potassium machine, one is sent to the argon machine. And that requires relatively large samples. It's a big downside, practical downside of the potassium-argon method. Now, potassium-argon geochronologists have come up with a clever solution to this problem. So they irradiate the sample with neutrons in a nuclear reactor. And in the nuclear reactor, potassium-39, which exists in a constant proportion to potassium-40, undergoes neutron activation to produce a synthetic isotope of argon, argon-39, which has a half-life of 269 years. So every atom of argon-39 in the sample is synthetic. There is no natural argon-39. We can then use this argon-39 as a proxy for potassium-39 in the sample. So we can substitute the potassium-40 for argon-39, and we can now measure an argon-argon age with one instrument. We only need to measure argon, so we only need an argon noble gas mass spectrometer. Now you'll note that this pre-multiplier here, this factor of 10%, has been replaced by a parameter J. This parameter J captures this branching ratio, but it also captures the efficiency of the conversion of potassium-39 to argon-39, which is a complex function of reactor physics, which is poorly understood. So if we want to calculate an age using the argon-argon method, we need to co-irradiate our sample with the standard of known age. If you know the age of this reference material, and you know the initial argon content, then you can calculate J. You can plug this J factor into the equation for the sample, and you can calculate the age. So it's like a relative method. The argon-argon method has largely replaced the potassium-argon method in geochronology, and is now really the main method that is used to calibrate the geologic timescale for ages of 200 million years and less, including the famous Cretaceous Paleogene boundary that is marked by the extinction of the dinosaurs. That's been dated with the argon-argon method. Okay, so let's now move on to the final 2 chronometers of the toolbox that I would like to talk about today. Both of these 2 chronometers are based on the radioactive decay of uranium. Uranium has 2 isotopes, 238 and 235. They exist in a constant proportion in the solar system. 238 is the heaviest atom that exists in the solar system today. It has 92 protons. That's why we call it uranium, and 146 neutrons. This atom is essentially too big for its own good and will, with time, fall apart into smaller, more stable atoms, notably lead and helium, where the helium is actually the alpha particles that are trapped in the mineral. When they acquire electrons, they turn into helium atoms. So we get two clocks for the price of one. We've got the uranium-helium clock, and we've got the uranium-lead clock. These tell us two completely different things about the history of our rock. Helium is a gas. It's a noble gas. It's the second smallest element on the periodic table. It's not happy sitting in the crystal lattice of a uranium-bearing phosphate or silicate mineral. With time, the helium will diffuse out of the crystal into the pore spaces of the rock, into the atmosphere, and then to space, because the thermal velocity of helium exceeds the escape velocity of planet Earth. It is only when the rock cools below 60 or 70 degrees that the helium gets locked in and that the clock starts ticking. So a helium age is a cooling age. Now, temperature rises as you go deeper into the crust. A temperature of 60 or 70 degrees corresponds to a depth of 2 to 3 kilometers. So the helium age tells us how rapidly the mountain, how rapidly or when the rock rose from depths of 2 to 3 kilometers to the surface. So if you measure the helium age of the summit of Mount Everest, you will get an older age than the base of Mount Everest, because the summit cooled before the base, and the age difference tells us how rapidly the mountain is rising. This is called thermochronology. And then finally, the fourth clock in my toolbox is based not on the helium, but on the lead that accumulates as a result of the radioactive decay of uranium. Uranium, as I said before, has not one but two isotopes, 238 and 235. They decay to two different isotopes of lead, lead-206 for uranium-238 and lead-207 for uranium-235, in the presence of a non-radiogenic isotope, lead-204. We can form two coupled isochron equations. So this makes this technique a bit more complicated, but also more powerful, because we've got an internal quality control in our chronometer. The uranium-lead method is the main method that is used to calibrate the geologic timescale beyond 200 million years. It has been used to date the oldest minerals on Earth, the Jack Hill zircons of Australia, which are 4.3 billion years old, and also all the materials, meteorites, that are found outside our planet. They come in many different types. The most primitive type of meteorite is a so-called carbonaceous chondrite. We've got very strong evidence that they really mark the formation of the solar system, and they've been dated at 4.57 billion years using the uranium-lead system. Okay, so those are the four chronometers that I will discuss in more detail in part 2 of my presentation. All these isotopic ratios of strontium to rubidium, of argon to potassium, of helium to uranium, and of lead to uranium, as well as many other chronometers, are based on atomic ratios of daughters to parents. These atomic ratios are measured on machines called mass spectrometers. These mass spectrometers actually don't measure atomic ratios, they measure electrical signals, and data processing and statistics is required to turn these electrical signals into estimates of atomic ratios. Here's an example of one such data set. These are raw data from a so-called ICP-MS, an inductively coupled plasma mass spectrometer. An analysis on an ICP-MS takes about 2 minutes. We've got 20 seconds where the laser fires into a closed shutter, so the instrument measures itself. And then we've got about 100 seconds where the shutter opens, the laser then releases atoms which are ionized and analyzed in the mass spectrometer. So in this case, I've got 3 isotopes of strontium plus 1 isotope of rubidium, which are tracked over time. You can see that the signals are affected by noise. So with this instrument, we can measure the ratios of strontium-87 to 86 and of rubidium to strontium multiple times. We need to average these ratios, and we need to quantify the precision of that to then be able to calculate ages, construct isochron diagrams, and so forth. Okay, so that was a whirlwind tour of geochronology. I will now revisit everything that I talked about in part 1 and highlight how all these issues, all these problems, all these techniques really are compositional problems at heart. Let's begin with that penultimate slide, the averaging of ratios obtained by mass spectrometry. So here I'm just showing one of the two ratios that were measured by ICP-MS, the strontium-87 to strontium-86 ratio. We've got multiple measurements which are affected by random noise, and we need to somehow average these ratios. So how conventionally mass spectrometer data reduction software does that? Well, it takes the ratio of strontium-87 to 86. In this case, that's 0.43. It does that for each step in the time series, and then we take the arithmetic mean of those ratios, and that gives us a value of 0.76. Now, the problem with that is that if you had chosen to take the reciprocal ratios, so the strontium-86 to strontium-87 ratio, then you would find that 1 divided by 0.43 is 2.32. But if you take the arithmetic mean of those reciprocal ratios, you get a value of 1.5. And 1 divided by the average of the reciprocal ratios does not equal the ratio. So 1 divided by 1.5 is 0.66, is not 0.76. So there's an inconsistency there, which surprises geochronologists, probably doesn't surprise you, but it is a big problem in geochronology that has long remained undiagnosed. Now, the solution to this nasty problem is very simple. Simply take logarithms. So if we take the logarithms of the ratios and we exponentiate the arithmetic mean of the logged ratios, we get a geometric mean ratio, which is 0.71. We can do the same for the reciprocal ratios, and then we find that the ratio, the geometric mean ratio, equals 1 divided by the geometric mean of the reciprocal ratios. And that's a much more satisfying result. All right, so this is a very simple example of how log ratios can help us out in geochronology. In the case of one isotopic ratio, let's now move on to the situation where we've got two isotopic ratios. So in part one, I introduced you to the isochron diagram, which is a diagram of, in this case, the strontium-87 to strontium-86 ratio against the rubidium-87 to 86 ratio. And I explained in part one that the intercept of a linear array of cogenetic aliquots of the same sample gives us the initial ratio, and the slope gives us the age. And this is where Felix Chayes comes into the equation, because Chayes warned geologists from the 1940s throughout his career to the 1970s. He warned geologists against diagrams of this type, because he pointed out in his book on ratio correlation, if you've got a diagram of two ratios with a common denominator, you can have strong, spurious correlations between the dependent and the independent variable. Now, I read this book as a first-year PhD student at Stanford University, and it's really this book that set me off on a journey to explore statistics and take modules in the statistics department at Stanford University. So I think it's fair to say that without this book and without Felix Chayes, I wouldn't be standing here today. And then, interestingly, all the equations in Chayes' book were actually derived by Carl Pearson. Carl Pearson wrote a paper in 1896 in which he introduced the concept of spurious correlation. Pearson is one of the founding fathers of statistics, and he established the world's first statistics department at University College London, the institution that employs me. So you will understand I simply had to talk about isochrons when receiving the Felix Chayes Prize. So if you're not familiar with ratio correlation, it's the curious phenomenon whereby if you have some uncorrelated variables, x, y, and z, just random uniform numbers, and we plot y over z versus x over z, which is the same as a rubidium-strontium isochron diagram, we can get these very strong positive correlations that are just an artifact of the way that we have plotted the data. This situation is entirely equivalent to the ICP-MS data reduction problem that I've introduced to you before. We've got three isotopes, we've got two ratios with a common denominator. So we must take into account this ratio correlation effect when fitting an isochron through some rubidium-strontium data. If we just use ordinary least squares regression, you'll get biased results. We also need to take into account the heteroscedasticity of the data, the fact that the uncertainties vary from one aliquot to the other. And this problem of weighted regression with correlated uncertainties was solved in the 1960s already by Canadian geochronologist Derek York. He used the method of least squares to solve this problem, but I actually find it easier to understand and generalize his method using the method of maximum likelihood. So here's the log likelihood function for this regression problem. The log likelihoods are written as a function of the misfits of the data around the best fit line, where you will recognize the equation for a bivariate or multivariate, but in this case bivariate normal distribution, where delta represents a vector of the residuals and sigma is the covariance matrix. The covariance matrix, which is responsible for the elongation of the error ellipses, that is the spurious correlation, the error correlation of the ratios discussed and quantified by Chayes and Pearson. Uppercase X and uppercase Y are the measured values, and here they're covariance matrix of the independent and the dependent variable. And then we've got n plus 2 unknowns. We've got the intercept A, we've got the slope B, and then we've got n, where n is the number of measurements, the number of error ellipses, values for the true but unknown value of the independent variable x. So we've got 2 times n measurements, we've got n plus 2 unknowns. We can solve this using the method of maximum likelihood, and that gives us the slope and the intercept and the age that properly accounts for the ratio correlation and the heteroscedasticity of the data. Now, in some cases, the ratio correlation can be very, very strong. This is the case when the denominator isotope is measured imprecisely. And that is here the case, for example, for this young argon-argon data set from East Africa. It's been used to date some high-profile human fossils that are too old to date with the radiocarbon method. We use the argon-argon method to date volcanic ash layers and date fossils like Lucy, for example. So here the argon-36 is a rarest isotope of argon. It's measured very imprecisely, and as a result, the error ellipses are very big and very elongated. It's quite frankly ugly, and it obscures the geologically meaningful isochron trend. So this occurs frequently in argon-argon geochronology, and to get around this problem, argon-argon geochronologists came up with this clever rearrangement of the isotopes to produce a so-called inverse isochron. So instead of using argon-36 as the common denominator, we use argon-40 as the common denominator. Argon-40 is more abundant, can therefore be measured more precisely, and therefore the ratio correlation is weaker. In this case, the age is not a function of the slope of the isochron, but of the horizontal intercept, because that gives us the reciprocal of the argon-40-39 ratio that you get from the slope of a conventional isochron. Now, geochronologists are convinced that the conventional and inverse isochrons are mathematically equivalent. In fact, they've written so explicitly in a paper, and indeed, in most cases, conventional and inverse isochrons give you more or less the same result, but that's not the case in all samples. So in this young rock from East Africa, from Kenya, we can see that the conventional isochron age is 71,000 years, the inverse isochron age is 74,000 years. It's not nice, and it's essentially the same problem as that reciprocal ratio problem for the strontium isotopes. In order to solve this problem of non-invertibility of isochrons, we need to recognize the fact that York regression allows the dependent and the independent variable to be, or expects them to be, Cartesian quantities that are free to range from -infinity to +infinity. Now, in reality, isochrons are correlating ratios that are strictly positive numbers. York regression is agnostic to that and doesn't take into account this positivity constraint. The very fact that we are interested in ratios tells us that the absolute amounts of argon 36, 39, and 40 are irrelevant. It's only the relative proportions that matter. So this forms a compositional data system, and we could renormalize the argon content of a rock to unity and plot it on a ternary diagram. That's what is shown here. So this is called a simplex, and the statistical issues of processing data that live within a simplex are well known to this community. Just very quickly, you cannot safely average data in the simplex. You cannot safely calculate confidence regions. This can produce results that are either unrepresentative of the data or physically impossible. We've got a physically impossible negative confidence bound for these 2 sigma polygons shown on the right-hand side of this slide. The problems associated with compositional data analysis, as you all know, were solved by John Aitchison, who established this elaborate system of log ratio transformations, and he showed that the problems associated with compositional data analysis can be solved by liberating the data from the confines of the triangle and freeing the data up to a Cartesian plane where data are free to range from -infinity to +infinity. There we can safely average data, we can construct confidence bounds and so forth, and once we've done that, we can safely map the results back to the ternary diagram if we so desire. So I would argue that we should do the same thing for geochronological data, for argon-argon data, but also for all other chronometers. In fact, before revisiting the isochron problem for argon-argon dating, I'd like to show how you can use principles of compositional data analysis for this other chronometer that I introduced in part 1, which is the uranium-helium clock. So uranium-helium in part 1, I explained that uranium-238 decays to lead-206 by releasing 8 alpha particles. Alpha particles, when they acquire electrons, turn into helium atoms. There are 2 other alpha-emitting nuclides that are commonly found together with uranium-238, and that is uranium-235 and thorium-232, another actinide metal, which all produce helium atoms. We can combine their ingrowth equations into one formula, where we've got the radiogenic helium on the left, and we've got the radioactive uranium and thorium on the right. This equation cannot be directly solved for T, but you can solve it iteratively. That's pretty straightforward. The important point is that the absolute amounts of uranium, thorium, and helium do not matter. We only care about the relative abundances of these 3 isotopes. So again, we can renormalize them to unity. And 15 years ago now, I proposed to the geochronology community that we should process the data in log ratio space, and, for example, average our data in log thorium-helium versus log uranium-helium space. We can then calculate the age corresponding to the average composition in log ratio space. I call that the central age, and if you like, you can map that result back to the ternary diagram. So that works for helium, and entirely equivalently, we can also apply the same idea to the argon methods. So we've got argon 36, 39, and 40, which can be mapped to a log ratio space. I would argue that all the data processing of the mass spectrometer data and the age calculation and isochron regression should take place in this log ratio space, and then, if you want, you can map the results back to the simplex. So, if we revisit York regression, on the left-hand side is the original York regression algorithm, which presupposes that your data are Cartesian quantities free to range from -infinity to +infinity. On the right-hand side is my adaptation of the York regression algorithm, in which I restrict the variables to the positive half space by simply taking logarithms. Solving this problem is now a nonlinear regression problem. It's no longer a linear problem, but it's still straightforward to solve using essentially the same approach as conventional York regression. And you can see that for my Kenyan ash layer data set, it gives exactly the same result regardless of whether you use conventional or inverse isochrons. So we are getting an improved accuracy, I would argue, by recognizing the compositional nature of argon-argon data. All right, so we've seen rubidium, strontium, uranium, thorium, helium, and argon-argon. Let's now move on to the fourth and final chronometer in the toolbox, which is based on the radioactive decay of uranium to lead. As I explained in part one, we've got two isotopes of uranium, which exist in constant proportion in our solar system, decaying to two different isotopes of lead in the presence of a third isotope of lead, forming these two coupled isochron equations. We cannot capture the system on a single triangle. We must use two triangles or a tetrahedron. So a slightly higher dimension of simplex, but we can still map that data space onto a Euclidean Cartesian set of coordinates of log ratios that are free to range from -infinity to +infinity. And again, I would argue that all data reduction error propagation should take place in this log ratio space rather than in the raw data space. And that works most of the time, but occasionally you run into problems, a problem that you're probably all aware with, which is the zero count problem, which does occur quite frequently in geochronology, because as I explained in part one, our data come from machines called mass spectrometers. Mass spectrometers are electronic devices. They've got detectors that could either be analog or digital. And digital detectors, such as this secondary electron multiplier, report data as counts. I've shown at the bottom of my slide an example of such a data table for three isotopes of lead, 207, 206, and 204. 204 is the rarest of the three isotopes. You can see that my table includes some zero values. If this zero is in the numerator of a ratio, then taking logs produces -infinity. If it puts it in the denominator, you get +infinity. In either case, the whole log ratio approach blows up in your face. There's been a lot written, said, and done about the zero problem. There are various approaches to dealing with zeros. I think the most appropriate approach in the case of count data is to recognize the fact that at a first step, the dispersion of the data caused by the counting is not really reflecting some logistic normal distribution. It's some discrete distribution that is underlying the counting statistics. Either a binomial distribution if you've got two components, or a multinomial distribution if you've got multiple components. So here's a Stats 101. We've got the binomial distribution, the number of counts of lead-204, and the number of counts of lead-207 in a particular cycle of my mass spectrum. Is a function of this parameter theta, which is a population parameter that describes a true proportion of lead-207 in my sample relative to total lead. So we can estimate theta using the method of maximum likelihood. It's a pretty trivial exercise. I won't go through all these equations. I actually broke it down into too many steps, but suffice it to say, it's very straightforward to show that the best in the maximum likelihood sense way to average count data is simply to take the sum of the lead-207 counts, take the sum of the lead-204 counts, and use the ratio of these sums as your maximum likelihood estimator, which incidentally is also immune to this reciprocal ratio problem that I mentioned earlier in the context of rubidium-strontium geochronology. So that's all very nice for a single analysis, multiple repeats within a mass spectrometer, but when you work with multiple samples from a field area or from a rock, it may not be safe to assume that our lead ratios are all representations of a single discrete value. If you have multiple samples, it is quite possible that the dispersion of the data does not only reflect counting uncertainty, binomial or multinomial counting uncertainty, but in addition to that, we may also have some true geological variability between one sample and another. We can test actually whether the counting uncertainties suffice to explain the dispersion of the data using a chi-square test. If your sample fails the chi-square test, if multiple samples are not consistent with just counting variability, then we can constrain the geological dispersion using a random effects model. A random effects model that mixes a, for example, logistic normal distribution for the true geological dispersion with the parameter mu and sigma square, with counting uncertainties added on top of that. So this is what the log likelihood function then looks like. It looks a little bit complicated, but you can recognize some exponents, square roots of 2 pi that remind us of the normal distribution. We've also got a binomial coefficient, which tells us that there's also some counting statistics in this log likelihood function. We can maximize this and we can infer some logistic normal population properties from a data set that includes zeros and includes counting statistics. So this equation here applies to the binomial distribution, but you can easily generalize it to higher dimensional cases, as is shown here for a ternary system of 3 components. Okay, now to conclude my presentation, I'd like to say a few words about error propagation. Analytical uncertainties are important to know in any discipline, but particularly so in geochronology, because knowing the uncertainties of our ages protects us from over-interpreting or under-interpreting our data. Error propagation is typically done by a first-order Taylor approximation. So if we've got some estimated parameter quantity z, which is a function of 2 measured quantities x and y, which could be isotopic ratios, then the uncertainty of z is given as a function of the uncertainties of x and y, as well as the covariance of x and y. This can either be written explicitly in this form here, or we could write it as a matrix formula. The matrix formulation is more easily generalizable to higher dimensions, but geochronologists have traditionally used this explicit form here. Now, it is very common in geochronology to assume that the covariance terms are 0. And that assumption is made for entirely practical reasons, because if you've got a function f of not 2 measured quantities x and y, but many, u, v, w, x, y, etc., then these covariance terms breed like rabbits, and they become very difficult to keep track of. So it's very convenient to just assume that they are 0, put your head in the sand, and carry on, which is equivalent to assuming that the covariance matrix is a diagonal matrix. Now, in reality, this assumption is rarely valid. We've already seen the error correlation that arises from the spurious effects described by Felix Chayes, but there are many other data processing steps that introduce correlated uncertainties, not only within an analysis, but between analyses. If you carefully work your way through this data processing chain, which I have done for the argon-argon method, you'll find that actually casting the whole data reduction process in terms of log ratios makes life a lot easier, because many steps in the data reduction chain involve multiplication. You take logs, that becomes addition. Or exponentiation, fractionation laws are exponential laws. You take logs, it becomes a nice multiplication. So it makes things easier to keep track of. And on the right-hand side of the slide, you can see the covariance matrix, or rather correlation matrix, normalized covariance matrix, of a large data set of multiple argon 36, 37, 38, 39, and 40 measurements in multiple samples, irradiation standards, air shots, and so forth, over the course of 2 weeks at the University of Melbourne. So again, conventional error propagation would assume that these covariance matrices are diagonal matrices, but in reality, as you go down through the data processing chain, the details of which don't matter, you can see that the error correlations spread like oil on water. And at the end of the day, your geological age, the uncertainty of the first age that you measured on Monday, is positively or negatively correlated with the uncertainty of the analysis that you measured on Friday, the week after. So everything's correlated with everything else. And it is very important that we get hold or get a grasp on those correlations. And that's really what I've been doing over the past 10 years, and what I plan to continue to do for the rest of my career. I'm writing, kind of creating together with colleagues an ecosystem of interrelated computer codes that process mass spectrometer data. There are many different kinds of mass spectrometers, many different kinds of applications, chronometers. We need to re-evaluate all of them in terms of log ratios. We need to capture these covariance structures, and we need to pass these covariance structures from one code to another. And together, this ecosystem will help us improve the accuracy and the precision of geochronology, and that will result in a better and fully traceable geologic timescale, which will benefit many other aspects of the earth sciences, such as paleobiology. So this is kind of an extension of the ratio correlation work that Felix Chayes did in the 1940s. And it's, yeah, so this is, Felix Chayes got me started on this journey. I don't know where it will lead me to, but it's been very interesting, and I'm looking forward to continue working on it. Thank you very much.
So before we go for the questions, perhaps a little bit picture with handing you the certificate.
Oh, right. Thank you very much.
Something to hang on your wall.
Oh, great. Well, shall I remove it from the plastic?
The other side.
Oh, it's already open. Right. Thank you very much. Yeah,
You're
cheers.
welcome.
If I'm not wrong, we have 10 minutes for questions. So is there any question in the room?
There was one there.
Is there a microphone? There's no other microphone.
I suggest that you take this. Turn that on.
I can shout.
No, exactly. So if you take that and then pick that pen, turn on. That should be on now.
Yep.
So first, thanks for the talk. I mean, it's totally not my field, and it was nicely presented. I could follow. And I have a few questions. The first one, so I get it that it's very mathematically beautiful that if we make the ratio in one way or in the other way, we get to the same conclusion. But why is this conclusion the right conclusion? I mean, I get it that it's mathematically beautiful, but I'm not more convinced that any of the others, in fact. Why this one is the right way? That's my question. And the second one is you assume, like you say, like for example, I think uranium, you say the ratio is constant through the whole solar system. How can you be sure of this? Are you God? I mean, like, I can imagine like even, I don't know, nuclear reactor. I mean, a lot of places on the Earth is not the case. In each atomic weapon, in each atomic reactor, and we could imagine natural stuff would do that. Or when you speak about meteorites, I mean, we can have meteorites who are coming from out of solar system, even if they're probably rare. I suppose they exist. So
Yes.
my question
Okay.
is...
Yeah, no,
like,
very good questions. So the first question was about how can we be sure that the log ratio approach is more accurate or is accurate? Right, so the first is, it's not just mathematical elegance. Many of these estimation algorithms assume that your residuals are normal. And when you look at the data that come out of a mass spectrometer, they're all skewed distributions. And just taking the log ratios makes everything more symmetric. And then your requirements for a maximum likelihood approach are fulfilled. I mean, all the statistical techniques that require normal distributions are fulfilled better than if you've got skewed distributions. Now, if you want to prove accuracy, you need independent age constraints. And there are ways. So there are, for example, in valve chronology, there are certain deposits of which we know the age independently. And that's how chronometers and the accuracy of chronometers is tested in general. we need to really to prove and convince you that the technique is accurate. We need to apply these intercalibrations of different chronometers to log ratio processed data, which I admit I haven't done, but it's something that definitely has to be done. Does that answer your question? But anyway, the current way, you've got two answers. They're definitely not both right. At least I've... yes. Yes. But so what I'm fixing is a statistical problem, and the statistics work better if you take log ratios, and the accuracy is a separate issue which can be solved or addressed using... Well, it's the eternal problem of precision versus accuracy, right? Precision, you can get a handle on with mathematics. Accuracy, you need calibration data. And that's what you need to do to demonstrate the accuracy of any technique, including log ratio analysis. And then the second question was about the uniformity of the 235-238 ratio in the solar system. That has been tested. So we do have samples from the moon. We've got samples from all kinds of meteorites. We've got samples from all kinds of rocks from the mantle, different lithologies. And the ratio of 137.818 is an average. There is some spread. There was a paper in Science in 2012 that documents the spread. So there is some fractionation between different parts of the globe, but it's a remarkably small range of variability. And the reason why the uranium isotope and the same any isotopic system that does not have radioactive parents tends to be pretty uniform throughout the solar system, especially the heavy isotopes. The lighter ones can get fractionated, of course, by low temperature processes, because they were homogenized in the solar nebula that preceded the formation of the solar system. So the solar system contracted out of a solar nebula. Within that solar nebula, mixing was pretty thorough, and so all these isotopes were well mixed. And this is actually the evidence that we have for the chondritic meteorites forming the basis of marking the birth of the solar system, because in these very, very primitive meteorites, we find that isotopes that are mixed and uniform in their relative ratios on Earth, they are fractionated between different parts of these meteorites. And for example, magnesium isotopes in very primitive meteorites, their ratios vary from one chondrule to another. And this tells us that these meteorites formed when radioactive aluminium-26, which has a half-life of 700,000 years, was still existent in the solar system. We've also got like plutonium fission tracks in very primitive meteorites. So we know that these very primitive meteorites formed within a few 100,000 years of the supernova that preceded the formation of the solar system. The Earth formed later, and everything's been thoroughly mixed. But in very primitive materials, you can find fractionation. However, not so much of the uranium isotopes, but of other isotopes that have short-lived parents. Okay?
Next question. There were more hands.
Thank you very much. Just a curiosity. So this covariance matrix might not be diagonal, but it might have some low-rank structure within it. So maybe if you add a diagonal plus a low-rank matrix, it might be able to model your data without having to use a full matrix. Have you ever experimented with this?
I haven't had to do that because the matrices are still manageable, but perhaps when you start building a geologic timescale with a humongous covariance matrix, because everything's correlated with everything else. For example, the potassium decay constant is determined by comparison with a uranium-lead standard. So the uncertainty of the decay constant of potassium is correlated with the uncertainty of the decay constant of uranium. So everything's correlated with everything else. And when we start putting thousands of analyses, tens of thousands of analyses that underpin the geologic timescale all together in one big covariance matrix, then I think clever maths tricks will be needed to deal with these large structures. So yeah. But I haven't had to do it so far. I'm just only getting started with putting together these matrices.
Any further short question? Well.
How would you suggest reporting the covariances?
Well, so the spider in this web of codes here records them as, well, you can record them as a flat table, right? And that's captured in a JSON file, but you mean you can record them quite easily. And,
messaging it to the next scientist in a way that the next software will understand it.
Well, yes, so that's why I propose using open text-based database formats. And for example, Isoplotter has that software has an input table. Traditionally, people had tables, recorded data in tables that have rows in which each row is a sample, and then a small number of columns with ratios, uncertainties, and one error correlation. What I propose is to add a whole bunch more columns with all these covariances, but you can still report it. It becomes a very big table, of course, but you can capture it in a flat data structure.